Hello and welcome to another session in physics. In this session, we'll be looking at the topic expansivity and its application. Under expansivity and its application, we'll be looking precisely at linear expansivity, area or superficial expansivity, and then volume or cubic expansivity. We'll also be looking at real and apparent expansivities, and subsequently we'll come to see what we call the anomalous expansion of water. But before that, let us review the previous lesson. Welcome back. Now, let's look at the definition of linear expansivity. This may be the first time you're hearing this term linear expansivity, or it may not be. But when we talk about linear expansivity, it has to do with the expansivity of solids linearly. So the standard definition for linear expansivity is that it can be defined as the increase in length per unit length per degree rise in temperature. Increase in length per unit length per degree rise in temperature. It is denoted by the Greek alphabet alpha, as you can see from your screen, and it is measured in per Kelvin. Per Kelvin is K raised to the power minus 1, or per degree Celsius. Degree Celsius raised to the power minus 1. So try to get that definition at the back of your mind. The fractional increase in length per unit length per degree rise in temperature. And it is denoted by alpha, like I mentioned earlier, and its unit is in per Kelvin or per degree Celsius. Now, let's look at this point, the mathematical representation of linear expansivity. The mathematical representation of linear expansivity is written thus: alpha equal to L2 minus L1 all over L1. Then you open a bracket and you show theta 2 minus theta 1. Now, what do all these things mean one after the other? Well, you know already that alpha is linear expansivity. That's what alpha stands for. Every material has its own expansivity. L2 is the final length of that material after it has expanded. L1 is the initial length. The initial length, how long it was, its length before it underwent expansivity. And then we have theta 2. Generally in physics and in other science courses, theta is used to show temperature. So theta 2 simply refers to final temperature, and theta 1 has to do with the initial temperature. So that's what it looks like. This is the mathematical representation of linear expansivity. At any point in time, you can make any of these variables the subject of the equation, depending on what it is you're asked to find. Alternatively, we can also say that alpha, which is linear expansivity, refers to change in length. So we use this called delta. This is a Greek alphabet called delta. We use it to show change in a particular quantity. Change in length, which is still the same thing as final length minus initial length, divided by initial length, which is always L1, times the change in temperature, delta times theta, or delta theta, to show the change in temperature. On the next slide here, let's try to look at a question that will actually apply and then see how far we can go with this. It says that a brass rod is 2 meters long at a certain temperature, and we're asked to find what the new length will be for a temperature rise of 100 Kelvin if the linear expansivity of brass is 18 times 10 raised to the power minus 6. So basically what they're asking us to find is the new length, L2. So the solution to this, already we know what we're asked to find. They asked us what the length will be after a temperature rise of 100 Kelvin. So we're looking for L2. We don't know what it is yet, but do we have L1? The answer is yes. L1 is 2 meters. And then the temperature rise refers to our change in temperature, which is 100 Kelvin. And then we have our linear expansivity, which is 18 times 10 raised to the power minus 6 per Kelvin. Alright, so for us to find L2, what it simply means is that we're going to make L2 the subject of the equation. And making L2 the subject of the equation, L2 is going to become equal to L1 bracket 1 plus the alpha times the change in temperature. That's what we're going to have to find our L2. So our L2 is going to give us L1, which is 2 meters, bracket 1 plus our linear expansivity, 18 times 10 raised to the power minus 6 times our change in temperature. Our change in temperature is 100 Kelvin. So we just have to complete this calculation by taking care of what is inside the bracket first of all. So for us to do that, we're going to have 2, and then we'll have 1 inside the bracket plus 18 times 10 raised to the power 6 times 100. Everything is going to give us 0.00018. So all we just have to do to find our L2 is going to become 2 bracket 1 plus everything here. Everything inside the bracket, when you add 1 to it, is inadvertently going to become 1.00018 because 1 plus 0 is 1. And then our final answer, which is L2, we say L2 therefore is equal to 2 times everything inside this bracket. Of course, 2 times 1 is 2, 2.0036 meters. And that's what our final answer is going to be. At this point, let's talk about area expansivity. Another name for area expansivity is superficial expansivity, and it refers to the fractional increase in area per unit area per degree rise in temperature, and it is denoted by beta and measured in per Kelvin as well. So this is the sign for beta. It's a Greek alphabet as well. And the mathematical expression of superficial or area expansivity is basically the same thing with that of linear expansivity, except that some things are going to change. And those things that are going to change is that instead of having our final length and our initial length, we're now going to have our final area, which is A2, minus our initial area, which is A1, all over initial area A1, and then inside the bracket you're going to have theta 2 minus theta 1. So it simply means that all those places we had L, we're just going to replace them with A. Instead of length, we are talking about area. And subsequently, we can have beta equal to delta A, that is change in A over the initial area times change in temperature, delta theta. And this is the mathematical expression for superficial expansivity. At any point in time, you can make any of these variables the subject of the equation to find any of them. And as usual, you know that beta simply means superficial expansivity. We've pointed that out earlier. Superficial expansivity, that's what beta stands for. And then of course we have A2. A2 simply refers to the final area. That wasn't obvious enough. A1 refers to the initial area as well. Anything that has to do with 1 refers to initial. And of course theta 2, we've made it clear that theta 2 is the final temperature and theta 1 is the initial temperature as well. And that's it. Once you know that theta stands for temperature and A is for area, you'll be able to do so well in this particular subject matter. And then let's talk about volume or cubic expansivity. When we talk about volume or cubic expansivity, we are simply referring to the fractional increase in volume per unit volume per degree rise in temperature. Of course, the symbol for measuring volume is gamma, the Greek alphabet gamma. Of course, linear expansivity was alpha, superficial or area expansivity was beta, and this one is gamma now. So using this to represent cubic expansivity, we're going to have the same formulas that we had before. So instead of having A or L, we're now going to have final volume minus initial volume all over initial volume times, and you open a bracket, theta 2 minus theta 1. Not that the times is entirely necessary, you can just put it there. Alright, so if we continue to consolidate on this, we're going to have change in volume all over V1 times our change in theta. And of course, at this point, you should know already that gamma is cubic or volume expansivity. And then of course, you know that this is final volume. And then you know V1 is initial volume. And theta 2, theta 1, I'll let you fill this up by yourself. It means final temperature and initial temperature respectively. At this point, let's talk about real and apparent cubic expansivity of water. Real or apparent cubic expansivity of water is represented using gamma and is subscripted R. When we talk about real or absolute expansivity of a liquid, we're simply referring to the increase in volume per unit volume per degree rise in temperature of that particular material that is being possessed by the container itself. On the other hand, when we're talking about apparent cubic expansivity, we are referring to the increase in volume per unit rise when that material, the liquid, is being heated in an expansible vessel. I'm going to tell you what this means on the next slide. So remember, we said this is the real expansivity and it is equal to the apparent expansivity plus the cubic expansivity. So I'm going to write it down. Real equal to apparent plus cubic expansivity. Now, if this wasn't clear enough, cubic expansivity, see it as the container itself. Cubic expansivity is the container, let's say the bucket or the basin. The apparent expansivity has to do with the content of the container. The contents of the container. Contents, let's say water that is inside the container. Then real is a sum of both of them, the apparent and the cubic. So in the real expansivity, you're not just going to have the water or the container, you're going to have both of them. So the real expansivity is going to be water plus container. So under real expansivity, we are not just looking at the container, we're looking at the contents of the container and how both of them expands in relation to each other. Whereas under apparent expansivity, we are only interested in what is inside that container. And then under cubic expansivity, we're not interested in what is inside, but we're interested in the container itself. At this point, let's talk about finally the anomalous behavior of water. We know full well that most liquids, almost all liquids, expand when they are heated. What it means is that when you put a liquid inside a kettle, for instance, let's say oil or groundnut oil, when you start heating it, after some time it starts to expand and make some cracking noise. This is to show you that it is expanding, and when you put the fire off, it contracts and the disturbance or noise goes down. But an exception is water. Water does not behave like this, and this is what we refer to as the anomalous expansion of water. You see, when water is heated from temperatures, it continues to expand and expand and expand. But you see, when water reaches 0 degrees Celsius, it is supposed to start expanding further. From 0 degrees Celsius to 4 degrees Celsius, it should continue expanding as well. But within this temperature range of 0 degrees Celsius to 4 degrees Celsius, something strange happens. Water begins to contract. Of course, when you're going from a lower temperature level to a higher temperature level, expansion should occur. And then when you're coming from a higher temperature level to a lower temperature level, contraction should occur. But in this instance, temperature going from small, which is 0, to big, which is 4, instead of expanding, it contracts. But beyond 4 degrees Celsius, everything comes back to normal and water starts to expand normally. This is what we call the anomalous expansion of water, and it takes place between temperature ranges of 0 degrees Celsius and 4 degrees Celsius. Thank you for joining us in this lesson. To refresh your memory on what we've just discussed, please take the test that will appear on your screen.